Okay, we should be live. Welcome everybody to what is, I guess, the first of it's not only is it the first virtual UK OpenInfra meetup, it's the first combined meetup of London and Manchester.
Yep, I believe that's true.
Yeah, sorry, I had YouTube playing in the background and it just started playing back my own voice to myself, which got very confusing.
And it's
so yeah, welcome.
We had Manchester meetup as well. I think over a year. Not that long since we had a London OpenInfra meetup, but it's been a fair bit of time at least. So it's good to have something back up.
The world has changed somewhat since the last London OpenInfra meetup. That's for sure.
Yeah.
Seems like something from an alternative reality somehow. So how's everyone doing then? How's lockdown treating everybody? How have you been, Danny?
I've been good. Yeah, been I mean, I've always worked from home, so that the change isn't drastically different, but obviously the life balance is what needs focusing on, and so I've been trying to get out and do things in spite of coronavirus, which I think I've been fairly successful for. I give myself a solid 4 out of 10. I've been okay.
Cool. So what else has been going on? Anyone managed to do get stuck into any interesting projects whilst they've been in lockdown? And what about yourself, Ildiko? Every time I bump into you at a meetup or an event, you're usually, you've been jetting here, there, and everywhere. So it must be quite nice. It must be quite nice to stay in one place for a while.
Yeah, on one hand it's nice, although on the other hand life is quite upside down and I'm not staying at the place where I planned to stay. And I would like to be reunited with my stuff that's at the place where I want it to be. So there are things like that, and I of course miss seeing people in person and have the fun parts of the events as well, and not just the talks. But doing my best to keep up with the communities that I'm participating in and trying to still see the people and interact with them any way I can. And I assume we're all trying to do the same. So yeah, I'm not jet lagged. However, sometimes there are calls and meetings at the middle of the night or the PTG running from midnight till 3 a.m. and things like that. So there is some similarity still, even though we are not traveling as much.
How have you been?
How are we going to go to the pub afterwards? Because that was half the point of the meetups, really, is to have a drink with everyone. And we can't really do that. We'll have to just have a glass of wine in front of the computer. But yes, no, everything's changed for me. So I've become, like many parents, I've become a primary school teacher. Unwilling, but had to be done. And also managed to be made redundant as well. So currently I'm actually unemployed, but interviewing with lots of people. So so things have changed a lot. Not so much the working from home, as you said, a lot of us would work from home anyway. But yeah, being a primary school teacher suddenly, and then trying to fit in half a day's work with half a day of teaching the kids has been a bit of a challenge. So not many new projects. It was winding down the last job, and so that's now finished. And so now I'm a free agent. So for a while at least. So I'll enjoy that while I can, have some time off. And I'm sure it'll be nose to the grindstone as soon as everything's settled down again, and I start with a new job. Uncomfortable silence here at the moment. So
who's organising this thing?
We haven't quite got it down pat, have we?
It's almost like we're a bunch of amateurs.
Well,
so what's going on with yourself, Mark? Are you getting up to much? How's life in Bristol?
Yeah, it's a bit different, I guess, like everyone else says, but in some ways it's nice. I've got a 1-year-old He was 1 last Friday, so getting to spend a bit more time with him and my wife is quite nice. Just getting to see him grow up and transforming from a tiny helpless little creature into a little guy that's on the verge of walking around and causing mayhem. So
awesome.
It's been quite nice in that way. It's obviously sad that his family can't see him so often, but they are now able to see him from time to time. So we're getting there. Spending a lot of time in this bedroom. I work in here in the day and I sleep in here at night.
Yeah. Cabin fever is definitely a real thing. Yeah.
Oh yes, yeah. Yes. I'm quite pleased with the relaxation of the lockdown rules a little bit, at least. I mean, we're not going mad, but I mean, just being able to go and see some other people finally is bringing sanity back, I think, rather than where we were heading, which was to be fat, drunk, and useless most of our days. Yeah, I think I've put on 2 kilos during lockdown.
What else is there to do? Drink and eat.
Yes. Who would have thought that it would have been okay to start drinking at 10 o'clock in the morning? I mean,
yeah.
Not that that's got anything to do with me losing my job, but anyway.
So we're going to start off with a bit of a chat about the fact that obviously this year is the 10th anniversary of OpenStack itself. And so maybe, I don't know, if folks have got any particularly memorable moments from the last 10 years with regards to OpenStack. What about yourself, Belmiro? Is there anything in particular that stands out for you with your time with OpenStack?
Hello, everyone. Oh, OpenStack, 10 years already. It's crazy. Memorable moments. I think we have so many. My particular case, my first OpenStack summit was in San Francisco. It was my first time flying there. It was one of the first summits, and those times were crazy. The community, the project, everything was starting, crazy new ideas. Everyone was extremely excited, building new things. It was very, very inspiring at that time. It led us to create our cloud. It was very, very exciting times. 10 years passed, and well, I think I continue excited with OpenStack. Now that we have CERN, big clouds, but there are still new things happening, and it's awesome to be in this great community.
Cool. Yeah, you must have. So that was pretty much near the beginning. Then there must have been an awful lot of excitement in San Francisco. The opportunity to build out something, pretty new and different.
Which year was that?
Maybe 2012.
2012, yeah. I was going to say 2012 was really where OpenStack got started. I mean, we were celebrating the 10th birthday to start 2010, but really 2012 was the first sort of release. Essex was really the first release that anybody could actually really get their teeth into. And I just joined Canonical at the time, 2012. And so I'd started doing some, general kind of sales engineering kind of stuff at Canonical. I had worked with OpenStack. I had deployed an instance on Diablo in, I think it was December. I got it working on my home setup kind of thing, and I could see the potential. And but 2012 and the Essex release, and then Canonical announced that they were officially supporting it, and then I started to, in theory, deal with real customers doing OpenStack deployments on Essex. How many real customers there were? Not many. You had to be a very early adopter to actually try things out in Essex. But it was great fun, and there was huge potential, and everybody could see the potential, and there was great excitement. And I'd say the next big event for me would have been the Paris summit.
Yeah.
Because it was Europe, everybody from the UK went, so you'd bump into everybody there. And Paris had, should we say, an obscene amount of money spent on it. And that was great fun being an attendee where big companies like Intel and HP were throwing money at you to get your interest, whether it was to hire you or to sell it to you or whatever. There was a lot of money being spent on trying to be the best show in town. And we're talking about Paris as well. We're not talking about some backwater town. We're talking about one of the most expensive cities in Europe. And Canonical, for example, hired out a whole museum for the night, which must have cost an absolute fortune. The rumours of the HP steak and champagne party are still legendary.
Yeah. The Argentinian beef and the Asian games and all kinds of that was definitely a memorable. I think if I think about memories of OpenStack, definitely Paris is one of my biggest memories, and also the Manchester Mid-Cycle and some of the meetups in Manchester. But that's only because they're quite close to home. But Paris is definitely the one that stands out for me, at least from my personal experience.
Yeah, I loved that one. That was great. And there was a lot of attendees. There was a lot of excitement. There was a lot of potential going forward, and people looking for customers and vendors getting all excited about OpenStack. And so it was a great time. But we were on that upward curve still. And we hadn't, if you know your excitement curves, you hadn't reached the trough of disillusionment yet. So so everything was very positive and on that upward curve.
When was the first time you started or you came across OpenStack, Görke?
Well, it was after Paris when things started to get serious. I don't remember the exact release when I started to deal with OpenStack, but I think it was like 3-4 years ago. And as I'm coming from the telco side of things, I was always involved in, the strange things and the difficult things and discussions. Also, I'm involved a bit in CNFA, so that doesn't make my life more easy in OpenStack environments. But that's the fun of it.
Definitely. I've just spotted a comment from Lewis Tucker on YouTube, by the way, Daryl. Says he hears you're available as a primary school teacher.
Yeah, well, currently, yes. Any job, please.
Maybe in a few years' time, when you've had some more practice, we can call on you.
I can actually get a job, yes, at a primary school. They were saying that there is a distinct lack of male primary school teachers, and it's mostly women in that industry, and there is a lack of male role models in primary schools. So maybe that's a future career direction for me. I hope not quite just yet, but yes. Thanks, Lewis.
So Daryl, you had a few slides that I believe you prepared as a retrospective of the London meetup.
Yeah, so I did put together a few slides. It's probably a bit too, I was going to talk a little bit and show a couple of photos, but really they're mostly things you would see elsewhere. But let me just sort of go through what I was going to say. I was just going to go through a little bit of the history as well. It is now Amazon launched EC2 in 2006, and we're 14 years into the cloud industry effectively, as that was really the launch of the major cloud movement. And then we got 2010, OpenStack comes along. 2012, we got the Essex release and supported OpenStack finally, and you know, people, early adopters, as I said, taking on OpenStack. But very quickly, people got on the OpenStack bandwagon, as it were. The 2013 Red Hat announced support on Grizzly. 2014 Oracle supported on Icehouse, and HP released their support in 2014 as well. I mean, the Essex release, though, really was the first one that anybody could take seriously. It was very exciting. It promoted an open cloud, whereas AWS and all the options we'd had previously were all closed service provider solutions. But expectations were extremely high, probably too high. But then we had the first London OpenStack meetup that year. Let me just show you that. There's going to be a transition while I switch to the share screen thing. All right.
So what year was the first London meetup?
It was 2012. Right, there we go.
Damn, I thought we'd pipped them to the post on it. I thought Manchester was the first meetup.
Oh, no. There we go. Right. So first time, no, July the 25th, 2012 was the first meetup. It's all there on meetup.com. You just look it up. We had it at Bluefin. Mark Baker was the organizer. He first started the OpenStack meetup in London with Canonical's backing, or Canonical paying for everything, basically. And we did it at the Bluefin building, which is Canonical's office, with great views of London, which you can see there.
Yeah.
Always loved that office. It was great.
It's a nice office. Yeah. Visited once, twice.
Yeah. So, I mean, we usually had the meetups 3 to 4 times a year. We had great community participation, lots of good venues. I mean, Black Rock, when we went there, that was the one that we had with the highest recorded attendance of 144. And a long list of sponsors who, you know, paid the bills, bought us all beer, and usually took us to an after meetup session in the pub as well, as you can see there. And we switched venues a few times. We mainly used Doggett's, which was a pub near Blackfriars. We had a couple of different rooms there, but we also used WeWork, the Microsoft Reactor. We even have Fujitsu's headquarters in London. They offered that up, their venue space for one of them. And then, of course, the Manchester meetup. Your first Manchester meetup was 2015, according to meetup.com.
That's right. I have got a picture somewhere.
Yeah, I nicked some pictures.
They're the same one. So the first one, Spaceport X.
That's it, Spaceport X.
Pretty awesome venue in Manchester that was great for this sort of thing whilst it existed. And good crowd, good turnout for the first meetup. Although I do believe that Danny had to drag a number of people from CodeThink along to actually make up the numbers. But yeah, not a bad turnout.
For the first one. Twisted a few arms.
I see. Yes. Pried them with beer and pizza. So, I mean, I put in a list of releases, but I'm not going to go through that. That's all a bit boring. But I did want to highlight... I typed that in wrong. But I did want to highlight the European Summits, Paris in 2014. Really enjoyed Barcelona in 2016, although I think the excessive excitement and throwing money at OpenStack had really got a bit more under control in Barcelona. And then Berlin, which I've typed Berlin there, but Berlin was what it's supposed to read, 2018. Again, another one. Felt a lot more intimate, that one, and it changed to the OpenInfra Summit by then. And then, of course, this year, 2020, we're going virtual. So there is no location, and we can all join at whatever ridiculous time in the middle of the night that they're going to have the talks. And then, of course, the last few years, we had the OpenStack Day in the UK, which started in 2017 with London. And that took a lot of effort to organise, and took a lot of my time to get this one up and running. And but I think after we got it running, it went. The day went very well. It was very well received. We had great attendees and good speakers. Lots of people travelling specifically to London for that day, and yeah, I think that generally went really well. And then, of course, we had one in 2019, which, because of the OpenInfra broadened things out, we had a lot more big users to come and do talks, as you can see there. And we also added, which I think was very good value for money, was the one day of workshops afterwards on things like Istio and Ansible and Kata containers, which I tried to attend as much as I could. And we had a couple of members of staff from where I was working at the time to attend those, and they were really useful training workshops at a bargain price, which was amazing. That's about all I've got, really. I haven't got any photos from that.
I think that's a really good summary.
Yeah. Okay.
Yeah, I do. So there was a call, like a 10-year community call that was posted to the mailing list a few weeks ago, which I had missed, and then Nick had prodded me halfway through and said, "Hey, do you know about this call?" So I joined a bit late, but it was really very wholesome and a really good summary of OpenStack over the last 10 years, and it was just, yeah, it was nice to look back at a lot of the memories, being part of the community, at least for the time that I have been part of it. So I don't know if any of you guys managed to join that.
No, didn't hear about it in time.
Yeah, unfortunately.
Yeah, too busy being a primary school teacher.
It was a great call. I was on. We had a few people sharing their memories about, well, the early days of OpenStack before my time. And I think it was really fun kind of hearing all sorts of perspectives of how people got into the community and what happened when the whole thing got kicked off. It was an exciting retrospective of how this all started and what happened since then. I think it was pretty great. And I also think that we had people from all around the globe giving talks. So good diversity as well.
I'd say one thing that was different for me about the OpenStack community was that it was very active, and there was a lot of people participating. I've been in open source for years, but the participation in open source tended to be, certainly in my experience, had tended to be more online and through IRC, which can only get you so far with organising people and relationships and so on. And seeing people face to face was obviously much better. And that was the first time really that we had attempted to help marshal that community ourselves as well. And that was so it was a different experience of open source than what I was used to.
That was one of the things that drew me into the OpenStack community. Really, was the community itself and how collaborative it was and how much excitement there was, and just the general welcoming nature of the community as a whole. And it's just something that's absolutely stuck with me. Yeah.
The face to face is definitely a big thing. I think it maybe had a lower barrier to entry because there was so many areas that you could contribute to, as opposed to, for example, the Linux kernel, where you really need to understand an area in depth before you're able to even make a single contribution. Although I never attended a UDS, Ubuntu Developer Summit, but I thought those were twice a year as well. Were they not, Daryl? Was there some similarity between those and Summit?
Basically, yeah, the Ubuntu Developer Summit was cancelled as the OpenStack Summit took over, and that was a conscious decision by Mark Shuttleworth. He didn't want to basically run the Ubuntu Developer Summit on a twice yearly basis, as well as the OpenStack Summit. So he basically picked the OpenStack Summit to be the primary, 6-monthly meetup for people. The Ubuntu Developer Summit was great. Well, I went to a few of those before they got canned, as it were. But it was obviously a different focus, and it's a focus on one company and one group of developers, all associated with that one, distribution. And so I'd say it was much less collaborative than the OpenStack events and summits and PTGs and so on. There's a much broader range of organizations involved, especially in the early days. There was a lot of organizations getting involved, and each could offer a bit of their specialism. So if you're a networking company, you would be interested in Neutron, and if you were a hosting company, you'd be interested in Nova, and so on. So I mean, there was a lot more collaboration than I would say at the Ubuntu Developer Summit. Yeah, it was much broader appeal.
It's quite hard to describe the community to people who aren't familiar with it, really, isn't it? Because it's so different from any other working environment. This kind of co-opetition model where you've got companies that are competing and collaborating at the same time, and there's a bit of friction, but the people on the ground, the developers, are mostly cooperating. I mean, it is quite an interesting dynamic and friendships.
Co-opetition, I like it.
Yeah, I didn't make it up.
But that's the beauty of open source, that you are working together with companies who are you are fighting with in the market, because you are sharing the same problems. You are trying to solve the same basic problems. So my example is that my first OpenStack contribution I made together with a guy from Ericsson. He helped me to finalize the contribution.
Yeah, and it's collaboration like that that really has made the community work properly.
Yeah,
and also challenges, I think, that no community has seen before. I mean, how do you deal with that many people contributing to a single project? How do you do CI in a way that makes sense? How do you have test infrastructure in a way that makes sense? I think there was some level of innovation in the OpenStack community, which I thought was quite cool. From the community management side of things, and from the kind of the infrastructure as well.
Yeah, and the infrastructure is a community as well. So if there was something that was broken, then anyone could go and try to figure out how to fix it. And I used to chat with the infra team 10 p.m. on a Friday night because I really wanted to get my stuff in, and the CI system was broken. So we tried to figure out what was wrong. So it was also a really nice experience to have all those people who tried to help, because I myself am really not a system administrator. So I wasn't always a huge help, but I was really, really motivated and enthusiastic about it. So it was really nice and fun, and still is.
Yeah, very true.
Cool.
All right, so I'm conscious of time, and we have a pretty packed agenda. So I think at this point we'll get cracking with the first talk. So yeah, we've got 3 presentations tonight. In case it's not already obvious, I realize I'm saying this 30 minutes into the stream already, but by all means, ask questions via YouTube chat. We get to see them in the streaming console that we've got, so speakers can answer at the end of their presentation. Yeah, I think that's all I need to say. So in that case, we'll hand over to Ildiko and Görke for the first talk on the Edge ecosystem, use cases and architectures. So if I start to drop a few of us out, and I can bring in your presentation.
In theory, I'm sharing.
Yeah, looks good.
Yay!
Make sure I've got the right people out. Okay, in that case, all yours.
Thanks. One of my first virtual experiences with giving a talk. I also have to mention that the platform is really burning the CPU in my machine. So if I disappear, then it melted off of the table. But hopefully it will not happen. First of all, if someone would not know us, I think we will start with a really quick introduction and then we will deep dive into the topic. So I'm Ildikó Báncsa. I started with the OpenStack community roughly 7 years ago. I've been with this community for a while. I was working for Ericsson at that time when I joined, and then I moved over to the OpenStack Foundation. I became an open source advocate and became a really big enthusiast about this whole community concept and working together and helping others to join and participate. I also participate in other communities like OPNFE, CNTT, and some others. So I'm really trying to also encourage people in different communities to work together, because I think that's also very important. I'm doing a lot of things with OSF, but one of the connecting items, I'm one of the, let's say, co-leaders of the OSF Edge Computing Group, and we will talk about that group a little bit later. And I'm also working with the Starting X community. It's a project supported by the OpenStack Foundation, and I'm sort of a community manager for them. It's also an Edge platform, so it's also kind of connecting to the topic. And with that, I would also like to give an opportunity to my partner in crime, Gergely, to introduce himself.
Hi, my name is Gergely Csatari. I'm working for Nokia in a small team dealing with open source in general inside the company. And within this OSPO team, I am the responsible for cloud infrastructures, meaning that I need to follow different cloud infrastructure projects, including OpenStack, Starlink-X, Kubernetes, and help Nokia to contribute to these projects. And this is why I'm involved in the OSF Edge Computing Group. And that is just a coincidence that both Ildikó and myself are Hungarian, so there is no rule in the group that you have to be Hungarian to be a member of the group. I'm also participating in CNTT and OpenInfra and some other open source projects related to cloud infrastructure, and some other open source projects related to management of open source itself.
Okay, then I think we can dive in. So I'm hoping that everyone sees the next slide. Let me know if not, and then we can jump into the troubleshooting part of the presentation. We chose the topic of edge computing because, well, an event cannot happen without at least one or two people talking about edge computing these days. So we took the opportunity to do that. And then you will hear much more exciting presentations after ours. But about edge itself. It would be and could be nice and easy if there was a definition of edge computing that we could just kick off the presentation with. I could put it on a slide and then we could move on. But that is actually not the case. And if people remember the good old days of cloud computing, and maybe it still happens, that was kind of in a similar situation in terms of what cloud computing means to people. I still heard a new explanation this week to it. And edge computing kind of takes it to the next level. And I personally like to describe edge computing as the next generation of cloud computing, because we are not introducing fundamentally new concepts or technologies here, but really taking them to the next level and also taking them out and closer to the users. Let them be human beings or machines, and really just get the whole world connected. So the whole thing is about taking the computing power and take it out as far from the traditional data centers as possible and make it available to everybody who would like to utilize it. And this practically most often results in massively distributed system over massively distributed systems, which means that we have a couple of challenges that we all know what they are, and we solved many of them one way or the other in some extent, but maybe we did not solve everything perfectly or fully, and edge computing definitely puts a highlight on these challenges and makes sure that we are dealing with things, for example, like interoperability, which has already been a huge headache in the past couple of years. And with edge computing, as these systems are usually growing kind of organically, it's something that will come back to the spotlight, and we will still need to make sure that this is something that is continuously addressed and we are providing solutions to it. Another aspect of edge computing is that it also kind of brings all industries into the IT space in some extent, and we will have a couple of use cases as examples to that. So it's not really IT only anymore or the mobile phones, but really much more than that, because practically we are all generating data in our everyday lives, and that data gets collected and analyzed in some shape or form. And with all that, there are all sorts of somewhat new things coming out, like privacy and security and how you protect that data. And when you look at edge computing from all this perspective, then you could provide a definition based on technology and this moving on the computing power, or you could provide a definition based on the security and privacy needs and all these type of aspects. So that's partially the reason that we don't really have one definition that works for everybody. And just in general, your edge is always different from mine. There's no question in that, really. So what we are trying to do with the edge computing group that we will talk about soon is to look at things from infrastructure perspective and trying to address the existing and also the new challenges in that space, and try to work together with other groups, let that be in OpenInfra or CNTT or in the CNCF ecosystem. So with as many groups as we have integration points with, to really make sure that we don't do double work, or that we are not solving the same thing at multiple places, because that's really just a waste of everybody's time, and then we all have to agree on the same thing all over and over again. Gergely, do you have anything to add to this slide?
Yes, one small correction, that your edge is not just always different from everybody else's, but it might be different from your other edges also.
Yes. That is very true. And I mentioned that I heard a different viewpoint about cloud computing this week. I was part of a discussion about edge, and someone brought up whether edge will kill the cloud or not. And in my view, it's not killing cloud, it's just sort of distributing cloud. But another opinion on that call was that practically cloud is something that is running on somebody else's machine. So it really wasn't the technology viewpoint and the software or even hardware viewpoint in that case, but really the privacy and where the data is, and that the data should not leave your premises. And in that sense, edge may in fact kill cloud if everyone will have their own data centers, and that will be the edge and the cloud in one place. So that's, again, yet another viewpoint that you can look at this whole thing from.
Just to add another spin to this, there is already like edge service by Amazon or Google Cloud, where you have the cloud located in several edge locations, but still operated by these other companies. So it's like it can be even like your own premises, but you get a box from a company and Edge is running there.
Yeah, it's just the more discussions and ideas and use cases we are having, the more definitions are out there and the more confusing this whole space is getting. But there are a lot of groups out there who are trying to find answers to all the questions that are out there. And if we have questions about the presentation as well, I will do my best with the screen sharing to recognize them, or we will take them at the end of the talk. One way or the other, we will make sure that we are answering them. So one of these groups is called OSF, Edge Computing Group. We weren't that creative with the name. It's also always hard to give names to groups. So this is practically a top-level working group that is supported by the OpenStack Foundation, and it's also sort of an abstraction layer higher than writing code. So our goals are to identify use cases and focus on the current ones that are either getting deployed in production or getting close to that, and identify requirements, trying to also group them, so find similarities and also differences, and define reference architecture models and see how we can put those together with existing software components, OpenStack, Kubernetes, of course, Linux, container runtimes, virtualization, all those things that are well known to everybody. And with this exercise, we are also trying to figure out a strategy and put testing into action as well, to be able to find gaps in the existing software solutions, and working together with other groups and communities when it comes to the implementation and also the integration parts. Our group is not exclusive to any industry segment. We are rather focusing on the infrastructure as a service layer, or, well, infrastructure in some shape or form. We are not looking deeply into hardware, but looking into connection points, and also not looking into applications, but looking into integration points as well. And we are also not exclusive to OpenStack, even though it's a group that is supported by the OpenStack Foundation. So we are really trying to be agnostic to technologies and look into what edge computing means and what the needs are, and how we can help the industry to address those needs. Among all sorts of activities, the working group members or participants are we like to share our findings and our work. So far, the group has produced 2 white papers, and the links are in the presentation. I assume that the presentation will be available somewhere after the event, or if not, feel free to reach out to Gergely or myself, and we will share this with you, all open content, or just take a screenshot of the links, and happy reading. And with that, if Gergely doesn't have any more to add to the working group itself, then I will switch to the next slide.
Yeah, just one small comment. So it's really an open group. That means that anybody can join, and anybody can be part of the discussion, and anybody can put their opinion into our material. So please join.
Please join. We have another slide that has some more information about how to participate. And also, it's not just talking. So we started to have some testing activities as well. So if you have hardware that you would like to run some edge-related software on, let us know. We are more than happy to utilize that and extend our activities there. Or if you're interested in that activity to help out and put these architectures together, that's even better. So please let us know. All right, and with that, we arrived to the use cases part. So kind of giving you a little bit of a better understanding that what edge computing might be and where and how it's used. So the first one is, guys, let me know when I should switch slides.
Okay, so yes, the first use case and like most important for me and other telecommunication people is the 5G and like generic telco use case for edge computing. And the motivation for introducing edge computing to telecommunication networks is to like find the right balance between the price of the hardware and the requirements of low latency and high bandwidth. So in telecommunication networks, we have like basically two big type of applications. The first type is just handling the control of the network, which means that these applications have they don't have too big bandwidth, but they are just sending controlling messages from here and there from time to time. But the other side of the network are the applications which are handling the user plane traffic, which means that they are really time sensitive and they handle big amount of data. And these two applications need a bit different kind of environment to run on. So in telecommunication networks, we don't even talk about like one type of edge clouds, but we are talking about different kind of edge clouds. So we are thinking about like the central data centers when we are running the central functions of the networks, like user databases and these kind of things. And as we move closer and closer to the users, we are running more and more the user plane specific applications. And in the 5G network, during the design of the network, this also was taken into consideration. So the virtualized RAN architecture, the radio access network elements were disintegrated in a way that the functionalities which are running, let's say, nicely in a centralized location are organized to a so-called centralized unit, which can run in an aggregated edge layer or even a regional data center. And the distributed unit of the radio access network can run in the access edge layers or even in the aggregated edge layer. So this means that every telecom operator can design their cloud infrastructure to run the telecom equipments according to the properties of the network. So it really depends on the size of the like the physical size of the network, like how big country do we have, and on the density of the population or the density of the traffic, and this can be designed in an optimal way. So because of this, edge computing is quite important for several aspects for telecommunications. And one very important factor of introducing edge computing is the level of automation what we have in these different edge computing environments, because without automation, we lose the benefit of using cloud technologies and edge computing. So automation is the part where we can gain operating cost from these systems. Other big benefit of introducing cloudification and edge computing for telecom equipment is the capability to scale these networks. So this means that when there is no traffic in the network, we are able to shut down and decommission specific parts of the network, or steer the resources to some other places or to other tasks when they are not needed for handling the traffic. So like one classical example is the stadium or rock concert example, when from time to time there is a big need for resources to handle traffic, but if the stadium is empty or there is no concert or any event, then these resources are not needed. So we can either run different applications on those resources, or we can just simply not use those. So we don't use energy to manage these or to run these resources. So based on these telecommunication use cases, we identified different requirements for edge clouds, and this is what we have in the next slide. And I just highlighted let's say the key requirements here. So one of the requirements is that we have high bandwidth and low latency need locally close to the users, and because of this high bandwidth and low latency requirements, we need the support of different acceleration technologies, which means that we have different hardware devices to where we can offload the handling of different specific tasks to the network, so we can have faster processing speed, basically for tasks specific to the network. Also, as I mentioned, we have different sizes and types of edges, and this is what I refer to when I mentioned that even your edge clouds can be different from each other, and edge architectures should be built in a way that they are really scalable and they are really modular in terms of both size and features. Also, because of the 5G requirements, we are talking about like hundreds or maybe in some cases thousands of edge cloud locations for one telecom operator, which really means that we have to solve the provisioning and management of these edge data centers remotely and in an automatic way. And this is what I mentioned in the last requirement, meaning that day zero operation is basically when you install the whole thing. So it should be possible to do it in a remote way without sending let's say experts to the edge clouds location. When the telecom operator buys the equipment, they should just like plug the network cable in and turn it on, and it should commission itself. And day one operation means that when the edge data center is running, all the operations should be available in a remote way to maintain the data center. And day two operation, I mean that when we would like to upgrade the infrastructure software, that also should be possible to do in a remote way, because in some cases these edge data centers are in really remote locations, and I think we will have an example about that in a later use case. So the next use case is industrial IoT. This is basically about like the thing what we call Industry 4.0 or the fourth industrial revolution, which means that our industry is now changing in a way that we are using more and more computing in the factories. We are using more and more automation in the factories, more and more artificial intelligence in the factories, which means that the factories themselves need some computing capability to run, for example, I don't know, some system which recognizes patterns in a video and can trigger some events. So there is no time in this case is to run the analysis in a central data center, but the analysis have to run on premise, but at the same time to keep the advantage of cloudification, this should be running in a cloud environment. So that's why it should be running in an edge cloud environment. So one example what we use, for example, one example what we use is like an automatic fencing of a robotic arm with video surveillance, which means that if somebody moves too close to the robot should stop, and we are doing that in a way that we are just like recording the movement of the robot in a camera, and there is a analytics engine which checks if nobody is close to the robot, and when people moves in the area where the robot is operating, then the robot is just stopped, and everything is calculated with analytics engine, and also of course we can upgrade it and change the algorithm and all of these things. So these are the applications what I'm talking about. Of course, because of the cloudification and because of these new architectures for IoT, the options are limitless. So because all of these devices are connected to each other, and applications can be built on top of these APIs which are provided by the different sensors and robots. It's really up to the use case, what kind of logic you can implement using these technologies. So the requirements for the industrial IoT a bit different from telco, of course, because in case of industrial IoT we don't have that high latency requirements. For example, in telecommunications we need latency requirements because of the strict timing of the physical interface itself. In case of industrial IoT, we don't have that constraint, so we have a high bandwidth requirement, but we do not have that low latency requirement. But also in case of industrial IoT edge cloud, it's possible that the edge cloud loses the network connection to the centralized location, but still the factory have to operate. So the edge cloud should work even if the connection to a central location is broken. And also because of the AI aspect of this, there is a need for the GPU support. So these are the two first use cases, and I hand over to Ildikó for the real remote use case.
Thanks. In the interest of time, I will do my best and really speed up. on the use cases, so we can talk about the architecture models a little bit too. Also, after hearing about both the telco side and the industrial side, it won't be fundamentally new, the other two use cases. With agriculture and aquaculture, I think the interesting part is that this is also an area a bit similarly to the industrial space, but maybe even a bit more, that is also going through the phase of digitalization and automation. So things that humans used to do are switching over to machines providing and performing those tasks. So the diagram itself shows some components from a shrimp farm where you need to be able to practically monitor the full life cycle of the animals and making sure that the environment is always suitable for them. And really from the larva phase to the full grown up, ready to harvest phase, you always need to be on top of the ponds, the different characteristics of the pond, and all the environmental circumstances, so that the animals don't get sick and don't die, because that's really bad for business, not to mention how bad that is for the animals themselves. So with all that, there are a lot of monitoring functions at these farms. Again, similarly to the industrial example, we don't have the robotic arm, but we do have to be able to feed the animals the right amount of food, monitor the pH value and the temperature, for instance, of the water, and all the other circumstances that appear. There is also the need for video surveillance, again, on one hand, to be able to monitor the stage of the ponds and the animals, but also to be able to send an alert and the report if someone breaks in who's not supposed to be there. So when it comes to video surveillance from the camera image, it is possible to identify if the person who's there is supposed to be there, or they are strangers who are breaking into a farm and trying to do something that they should not. So all these tasks are starting to be performed by machines only. So machine learning and AI plays a bigger and bigger part in this industry as well. And in that sense, you need the computing power. And again, you need autonomy here too, because in more centralized, bigger data centers, you can do a lot of analysis on the data, but you also need to make sure that the immediate reaction is also there within the system locally. So if the connection loses between the central site and the local data center next to the pond, then the animal's life cycle won't be interrupted by that. So as you can see, there are a lot of similarities to other use cases, but it's still its own unique use case as well. So not everything is the same. But as I mentioned, the autonomous operation is one of the most important parts of it. And with all that, the network disruption, the system needs to tolerate that, so that we can all eat a lot of shrimp because it's delicious. And with that content delivery network, I don't think that I need to describe this one in a lot of details. I think most of us are using this in some extent. I just got a new package with unlimited data yesterday, so I'm excited to see if everything will keep on working when I'm, for example, taking the bus home and trying to stream some content. the edge relevant parts of content caching is more around the side of how you distribute the content, how you make sure that most of the content request gets served from an edge location, practically one that is really close to the user who's trying to access that content. So kind of planning and action based on information such as, for instance, location or the load of the actual node. If it needs to do video transcoding and has serving a lot of users already, then you may want to have the new requests served from another near site. So really how you distribute the content and how you provide flexibility into the system without overloading the backbone network, which can be a challenge in this case. And you can see some requirements: high bandwidth, as I said, the monitoring of the nodes and the load on those nodes, and location awareness are some of the key requirements of this use case. And with that, we reached the architecture models. So jumping into that one, before we go into some details, I would mention that the Edge Computing Group has been working for 2-3 years to identify different reference architecture models. Our goal is to find the minimum amount of different models that would cover most of the use cases, but we recognized it quite early on that there is no one-size-fits-all solution, especially because everybody's edges are different from their own and everybody else's all the time. And also in most cases, these environments, the infrastructure looks like a big spider web. So when we talk about the edge nodes and the edge parts, they are usually connected to a central, a regional data center. And with that, when you look at the whole connected distributed infrastructure, you will find a lot of challenges that will be different in case of the different use cases. For example, the requirement towards the autonomous operation of an edge site. Do you need that? Or if you lose the network connection, you're good if the workloads are still running until the communication is back up. And then you can synchronize the data between the central site and the edge site once it's back, and you can store it in the meantime, the filtered and aggregated data that you would send up. So we are analyzing these kind of requirements, and we came to 2 models, the centralized and the distributed control plane model that Gergely will talk a bit more about. And here I would also like to mention that if you have a use case or an environment, a system that would be different from these, or you have any input to the existing models, then please share it with us. And with that, back to Gergely.
Yes, so as Ildikó mentioned, we drafted like 2 architecture models, but it's possible to have some kind of a mix of these 2. But let's just cover these 2 like big types of the models. So we are differentiating these models among the place of the control plane, and here I mean the control plane of the infrastructure itself. So in the first case, the control plane is in a centralized place, and in the edge data centers we do not have the control plane part of a cloud. We have only the components of a cloud which are needed for the worker nodes. Nothing else is running from the control plane in the edge data centers. The benefit of this is that the footprint of the edge data centers can be very small. This can go down into a single computer, even with a limited resources, and it's also easier to orchestrate the whole system in this architecture because there is no need to synchronize between different controllers. The drawback of this architecture is the edge sites are not autonomous. So if they lose the connection to the central location, they will stop operating. This does not mean that the workloads will suffer. This means only that there is no way to change the state of the workloads. This what we call like to do lifecycle management operation on the workloads. But this can be a problem in some of the cases, and also there is a reduced functionality in case of network failure in the edge data center. So as we mentioned, this architecture is good for some use cases and not good for some other use cases. This is why we have another architecture model, which is the distributed control plane model, which means that in every edge data center, there is a full control plane of the cloud, which means that that all the components to run the cloud are running in the location. So as a consequence of that, the locations are autonomous. So even if there is a network connectivity loss between the external world and the edge data center itself is fully operational, and all operations, including the lifecycle management operations of the workloads, can be executed. However, on the other side, in case of this architecture model, the resources are needed to run the control plane of the cloud in the edge data centers, which can be, let's say, a serious amount of resources if we are talking about edge use cases. Also, there is a thing what we call orchestration overhead, which means that there are some data what we need to synchronize between these controllers in the edge cloud infrastructure to make the whole infrastructure consistent and to ensure the automatic operation of the edge clouds. So these are the two big architecture models, and both of these can be implemented with both OpenStack and Kubernetes. In the Edge Computing Group, we are having examples for the implementation with OpenStack, and now we are start to work on an implementation, let's say, example with Kubernetes. And with this, I hand over back to Ildiko for verification and validation.
Thanks. I would also like to highlight that we are also looking into how we can combine OpenStack and Kubernetes services and any other software component that fits into the system that fulfills a need or requirement that's needed by the use cases we mentioned earlier, or some new ones that are in flight these days. As we are kind of out of time, I will just quickly mention the testing considerations that we've been having. We had some activities so far to build both reference architecture models. One is with Starling X, which is more of the distributed control plane scenario, and the other effort was using the distributed compute node setup from OO, which is more of the centralized control plane setup. And we only did some basic deployment and just evaluating that, in fact, the concept works. Each of these examples have some of their solutions and feature additions in terms of how to fulfill the requirements and build out the characteristics of those systems. And our goal is to continue the testing activities. And with that, one of the big challenges is obviously the scale, because a lot of these edge deployments, like if you look at the 5G one, for example, it's a large scale and also geographically distributed example. So how do you make sure when you're testing that your system and environment is prepared for those kind of circumstances as well? And the other interesting challenge with testing is acceleration devices in terms of hardware, how you have access to these kind of devices, and how you can perform the testing activities with those, because you cannot emulate everything. And obviously, we all like to have our hands on these devices because it's really exciting to be able to do some testing with these involved, and they are really important for many edge computing use cases. And obviously, you would like to be able to do testing in a mainly automated way and making sure that you can repeat the action, and others can also build the test environment and will get to the same results as you did if they also did the building the same way. So we are trying to move forward towards this direction, and kind of really making sure that on one hand we are testing the existing simple functionalities and kind of making sure that they are available on the edge sites, really just simple things like creating or deleting a resource, or testing the distributed virtual router functionality, for example, for the centralized model is another example towards the distributed nature of these environments. And then, of course, we talked a lot about what happens when you lose network connection. And obviously, you would like to test your system that it really behaves the way as you would expect it. And these are the ways forward where we would like to move, and would love to get help from people who are watching this talk. So in terms of how to participate in the group, you can find all the resources on these links. We have weekly calls, IRC channel, and we are showing up on all sorts of events. And with that, I apologize that we talk a lot, and I think we are very over time, but also done. And with that, also, I think we can address questions offline after the event or in parallel. Find us on IRC and or email. And thank you for having us.
Thank you. It looks like we have a question. How close are we to fully decentralized deployment? Is this a real thing we are starting to see in the wild?
When it comes to fully decentralized, I mentioned Starling X. It is a platform that is trying to address that architecture model, and they have a distributed cloud feature that tries to address the challenges that the decentralized deployment gives to people to work with. And I also heard about a solution. It's not starting X. It's a different concept where basically they have a lot of separate OpenStack deployments and one management and orchestration component centrally that manages all these separate deployments. And as far as I know, they are deployed in production or really close to that. So it does exist, but still have a lot of things to do to make it much better. As
Yes, I agree with that.
Cool. Well, that was a very, very interesting summary. Thank you for walking us through that. So, if we don't have any more questions, I think we should move swiftly on to our next talk, which is Mark, who's going to walk us through Kyobi and Collar and sane OpenStack deployments.
Okay. Hi, everyone. Thank you for that, Ildiko and Gergely. That was really, really interesting talk. I know that Edge is quite a hot topic these days, and it's interesting to see where the working group's taking it, and to see some different approaches to solving that problem. It's definitely it's a problem space we're starting to dip our toes into. So I'm working on a project that is got Edge in the name, so that's interesting.
Is that with Collar?
It is, yeah. I'm sure that edge is different to the edges that have been described today in some way. So hopefully you can see my slides.
We can.
Great. So today I'll be talking about Kyobi and Collar and how to deploy OpenStack in a sane way. I'll cover a little bit of history of the projects, talk a bit about Collar, and then Kyobi. We'll have a demo, and then a little bit about the community. So I work for a company called Stack HPC. We're a Bristol-based consultancy that focus on high-performance computing and cloud and where those two things meet. I've been working with OpenStack, both downstream and upstream, on development and operations since 2014. And in that time, I've picked up some cool reviewer hats in Collar and Ironic. And for, I think this is my third cycle as Collar PTL. So that's been quite an interesting journey to see things from that perspective. And this is, well, I guess I can't lie about my appearance, seeing as you can see me on video, but that's an artist's impression of what I looked like about 8 years ago. So let's start with some history. In 2014, I was working for a company called Cray. Cray is known as the supercomputer company, the kind of the creator of high performance computing and the huge machines that go along with it. Really interesting place to work. And in 2014, they tasked the Bristol team with investigating OpenStack. We had the cluster that you can see on the right there. It didn't look quite like that at the time, but essentially a bunch of PC motherboards without cases mounted directly onto sheets with desktop power supplies, all plugged into some pretty simple switches, but it was enough, and it got us going. So we started with OpenStack Habana. We went through the manuals, and we instruction by instruction got it going. We even deployed the system as a bare metal compute platform using a very early version of Ironic, which is the piece that I was involved with. In that process, we created the Ironic SNMP power driver because, as you might imagine, those desktop PC power supplies don't have any out-of-band control. And on the bottom left, you can see a screen that over the years I've become quite familiar with. Failing Pixie boot. So moving on, we, having tried out OpenStack, we decided, yes, this is the thing for us, and tried to do it in a more professional manner. So we started out creating an OpenStack package distribution using a tool called Anvil that's no longer around, which creates RPMs from Python packages. And it was a bit of a nightmare, as you might imagine. Dependency hell. We used a project called OpenStack Ansible to automate the deployment. And this is not the same project as OpenStack Ansible that is in use today. We were focusing on bare metal compute with Ironic. And over time, we partnered with Mirantis and built a pretty advanced set of provisioning capabilities using originally the fuel agent, which became a project called Baryon. And to this day, it still has some capabilities that don't exist in Ironic. It's quite impressive. We needed to cover diskless and diskful boot. So the traditional way of booting a high-performance computing cluster is without disks and having something like an NFS mount to your root file system, which means you can provision them very quickly. You boot them up very quickly, and they all share a consistent environment. But for some of the other types of utility nodes, we needed to support provisioning to disk, and that's where the provisioning capabilities of the Baryon came in. And there are a couple of talks we got about what we got up to in those days. So 2015-16 timeframe, we realized that we'd backed a dud. This OpenStack Ansible project, although it looked promising at the time, it was a bit of a dead end. The development had stalled, and there were other projects that were popping up that were looking more interesting. We realized that without containers, upgrades are pretty hard. If you've got a single set of packages that need to be consistent across the system, then updating things one at a time is next to impossible. So we decided that containers were the solution to all of our problems and decided to pick a new deployment tool. A bit of a survey of the available tools offered up two candidates, Collar Ansible and OpenStack Ansible. And that is the OpenStack Ansible that we're familiar with today. So what happens? We run a bake-off. Collar Ansible versus OpenStack Ansible, and I disappear into a hole for 3 weeks, trying out these different tools and writing a fairly giant report on the differences between them and how they might be suitable for us or otherwise. And if you saw the title of the talk, then no surprise, we ended up with Collar. Now, I'll talk a little bit about how we came to that decision, or the reasons behind that decision later on. And it's not to say that OpenStack Ansible isn't a great tool. It certainly is, and it's come a long way since 2015. But I think that Collar was a better fit for us. So forward to 2017, and I'm now working at Stack HPC. And one of our early projects was for the Square Kilometre Array. Now this is a really fascinating global project, multinational. They're building two huge telescopes, radio telescopes, in South Africa and Australia, and they need a giant computer to process them, which they're calling this Science Data Processor, SDP. And so we were involved in building the prototype platform, not necessarily for the SDP, but for the technologies that might go into it. So testing out the hardware and the software. So we've got 2 racks of bare metal compute that we need to provision and manage. We've got various different types of nodes, some with high memory, some with NVMe, some with GPUs, different types of networks, all the way from 1 gig to 100 gig EDR InfiniBand. And we need to tame this and manage it using OpenStack. So we decided to go with Collar Ansible based on previous research and our experience with it. And we ended up building KOB to fill some of the gaps in that tool. So 2020 today, KOB is an official OpenStack project since the train release. It's part of the Collar project, and it allows you to deploy OpenStack in containers on bare metal. And it's now used in production at many sites around the world. And something that's really nice to see is people picking this up without in being affiliated with Stack HPC. It's one thing to sell to build a tool and a community around it, and to use that to deploy it the sites of your clients. But for other people to validate your choices and pick it up and run with it, I think the furthest is in Australia. That's really cool to see. So I'll talk a bit about Collar. The mission of the Collar project is to provide production-ready containers and deployment tools for operating OpenStack clouds. It's been around since Kilo, joined the big tent in Liberty. And one of the nice things about the project is that it's not sponsored by a single vendor, and there's a hugely diverse contributor and user base. And it really feels like a proper open source project. There are 2 main projects, or 2 main deliverables that are part of the project, and Collar is for building OpenStack container images, and Collar Ansible for deploying those images using Ansible. Collar supports various different distributions and server architectures. It's very customizable. You can add various different plugins. You can say, I want this package repository to be added or removed. I want to add this particular package to this container, or even remove a package to trim down the size of the image. And you can inject arbitrary commands at various points in the Docker file. So it's pretty flexible. We build the default images every day for every release supported and master, and push them to Docker Hub. Collar Ansible takes those Collar images and deploys them using Ansible. The architecture that it uses is highly available and scalable, and it's got a really broad range of services that it supports, over 50. It's very customizable. You can set pretty much any config option using the native ini file format, which is really nice because there's no translation layer. You just go to find your configuration reference for Nova, for instance, grab the section, the option name and the value, and using the native ini format, pop that into your configuration directory. The reference architecture looks a bit like this. We've got HA proxy, load balancing access to the API servers. KeepAliveD provides a virtual IP and failover, representing a generic OpenStack service in these blue boxes, which might have workers on the control plane and agents potentially distributed throughout the compute nodes. And then, of course, we've got networking, message queue, database, and compute hypervisor. So we often talk about the what, but it's quite important as well to discuss the why. Why do we do it this way? And I suppose, first of all, why do we deploy OpenStack in containers, and in particular in this application container pattern, which is pretty much ubiquitous these days. I think when people think of containers, they're kind of the original Docker model of a single process. Well, the reason we do it this way is that using images, immutable images, makes things repeatable. You can build a set of images once, you can test them, and then you can use the same images in a different environment. Another great thing about having images is that you can do all of your installation at build time, pull those images down in advance, and there's no installation required at deployment time. It's literally just a case of creating a container from an image. Containers make things scalable. You can have improved isolation. And I think the big one here for OpenStack is file system isolation. So we can isolate the dependencies of different services, which is really helpful for upgrading. And it even means we can run different versions of services alongside each other. We don't do networking isolation in Collar, and really that's it's just to keep things simple. We use host networking. You can end up with quite a mess of bridges and IP tables, rules, and other things in your container networking environment, which, yeah, I guess they might add some network isolation, but I think for OpenStack, I feel that the trade-off is probably not worth it, given the amount of complexity that exists already, particularly in terms of networking. And containers do make it possible to do rolling upgrades, quickly replacing one container with another. So why Ansible? It's pretty ubiquitous as a configuration management tool these days. And it's, in terms of OpenStack, certainly it's relatively simple. You can, it's easy to understand. You can look at a playbook, and even if you don't really know Ansible, if you have a rough idea what YAML looks like, then you can figure out what it's doing. It's predictable. That the imperative order of execution means you know what's going to happen. There's no race condition involved generally. And the deployment of OpenStack is complex enough of a workflow that I think it really just makes sense to do things carefully, even if it takes a little longer. OpenStack isn't really a cloud native application. It was built before that time. And you can bend it to fit into Kubernetes, but I don't know how happy it is being there. I quite like the static placement of Ansible, knowing that we can say that a container is definitely going to land on a particular host and stay there. And with Ansible, we do get quite a lot of fine-grained control. So we can say only execute on these specific hosts, only manage these particular services. And we might even say something like upgrade do a minor upgrade of Nova, for instance, on this compute node. And that's perfectly possible. So having covered Collar, let's move on to Kobe. Why did we build it? What's missing from Collar Ansible? Well, one of the nice things about Collar Ansible is its simplicity. It really focuses on one problem, which is how to deploy OpenStack in containers. And that really helps to make it understandable. But it does mean that there are a few things that are missing if you want to provision a cloud from scratch. It, for the most part, assumes that your hosts they're up, they're deployed, and they're running Docker and ready to run containers. There's no support for bare metal provisioning of the cloud hosts, the controllers, the compute hypervisors, the equivalent of OO's undercloud or director. There's not much in the way of configuration of your control plane host OS, things like your networking, your storage. And there's not much in the way of management for bare metal compute nodes, which is something that was quite key for the SKA project. The name comes from KOB, Collar on Bifrost. And it adds these missing pieces. It uses Bifrost to provision the bare metal controllers and hypervisors with an operating system. It then configures that operating system and gets it ready to run containers. It supports management of physical network devices. So if you want to give KOB control of your network, then it can set up a static configuration. It's got support for driving Collar Ansible, generating an inventory for it and configuration, and for defining where services are placed. And it's got some support for managing bare metal compute nodes. It uses the same underlying library as the OpenStack CLI, so it's got a pretty consistent interface. And it's all written using Ansible playbooks and Python with a Python CLI. The stack looks a bit like this. So we've got the CLI wrapper on the top, and that calls down into KOB playbooks. We've also got the red boxes, which are running on a host we call the seed, and that's where we run Bifrost and Ironic for provisioning. It uses Collar for building container images and Collar Ansible for deploying those images. So let's take a look at the hosts in the system and how they relate to each other. So we start off with a host we call the Ansible control host. This is generally where the operator logs in and executes KOB from. And they can use this host to configure the network devices if they choose. I know that not every environment is happy with allowing arbitrary access to network devices, so that this might be something that your networking team does. We then deploy a seed host, and on that seed we run Bifrost, which in turn runs Ironic. And the seed will provision an OS to the control plane and the hypervisor hosts. We then use Collar Ansible to deploy OpenStack services on those hosts. And finally, if you're using bare metal compute, then your control plane can provision those machines for user workloads. So this is a diagram that that we put together just to show how this works on a larger machine. So we've got 3 racks. Got some top of rack switches, core switch, got a single Ansible controller host in green, a seed host, and we can see that the seed is provisioning these machines in turn for the control plane, for storage, for the virtualized compute hypervisors, and then eventually we end up with user workloads on bare metal compute. Now it's not specifically for bare metal compute we support. That's an optional extra. I know that it's not in use everywhere. So the network device management, managing switches and routers, is done using Ansible's network configuration modules, and it applies a static network configuration that we define in the Ansible configuration. The devices are added as hosts to the Ansible inventory, and host variables define the configuration. On the seed host, we run Bifrost services. That includes Ironic and everything else required to run the provisioning environment. And if you're familiar with OOO, this is similar to the undercloud. We've got automation to deploy this as a VM on top of a hypervisor. And the resource requirements for this machine are not huge, so this is quite a nice way to make use of a single machine for multiple tasks. So in terms of OpenStack, you might call Bifrost a minimal bare metal provisioning environment. It's got a handful of services, and it gives you everything you need to build an image, to dynamically boot up an agent on those machines, and provision that image to the machines. It again uses Ansible, so it's familiar to the user. And we can use this to do discovery and inspection of the control plane nodes, and then to deploy them with an image. Once we've got our machines provisioned with an OS image, we can start to configure them. And this step takes the machine from a raw provisioned image without configuration to something that's ready to run containers. And we've tried as where we can to reuse roles from Ansible Galaxy. So we do some bootstrapping of the user environment. We support static configuration of the network. We can support Ethernet, VLANs, bridges, bonds. We can set up DNS, or network time. Various ways of controlling the storage on the system. You can do an initial wipe of the storage, other than the root volume, of course. We can use Lux for disk encryption, software RAID, or LVM. If you're using Device Mapper Docker storage, then we've got tools for setting that up. And also, it's possible to create user accounts on the machines. So what does it look like when you're using KOB? So here are just some examples of different commands that we might use. This first one we use to provision the control plane hosts. The second one we configure host OS services, and we're using the limit argument to only do that on compute hosts. The third example, we're deploying only Ironic. And this is quite nice. So you can make a change and you can be confident that you won't affect any services other than Ironic. When you're upgrading, sometimes it can be nice to do things, services one by one. I know that certainly places like CERN will do this. They wouldn't upgrade everything in one go. They would upgrade services one by one. I'm sure Belmiro will be talking about that later on. But in this case, we're upgrading Keystone, and then after that, we might want to run some tests against the system to make sure that everything's happy. This command at the bottom is quite nice in that we can fetch the configuration that's been generated for every service and pull it down to the Ansible control host. And you can combine that with another command to do a generation of configuration, which allows you to compare two sets of configuration before and after a change without actually applying it. So one of the things that we do, the way that we work, is to make all of the configuration version controlled. So we've got this KOB config repo, and this tracks a set of default configuration files, which any environment would make a clone of, add their configuration to it, and track their configuration changes over time. And we've got various different things in here: YAML configuration files, your Ansible inventory, collar configuration, and in fact, it's often a place to keep other things like certificates as well. We've now got support for adding custom playbooks that are specific to a particular site, and we track those in this KOB config repo as well. There are some examples here that you can take a look at. This SKO one is the first one, Alaska. So, as promised, let's have a little demo. What I'm going to show to you today is something called the Universe from Nothing. Now, this was originally a workshop from the Denver 29 Sane Summit. You can go along to this Git repository on GitHub, and it's got instructions in the README there to follow along on your own. And it's basically one of these KOB config repos that are mentioned here. And there are a few small scripts to set up networking of things. As you can see, there's me on the front left, and people are loving it. They're having a great time. This is a bit of a simplified view of what the lab looks like. So the grey box is the host that you're running the lab on, which could be a virtual machine. Needs to be fairly a beefy one, but in this case, I'll be using a bare metal machine. And we've got 3 virtual machines running inside it. These are connected up by a single bridge, BR-AIO, and that has access to the outside world. So we've got our seed on the left running Bifrost and a local registry. And we've got a single controller and a compute node. And these are both running containers. And then this green box, demo 1, is a virtual machine running on the compute node. So hopefully you can see my screen. This is a bare metal machine, and with a Blue Peter demo in that. Here's one I made earlier. Now, you might notice this is a slightly supercharged version of the diagram I showed you previously, in that we've got 3 controllers, 3 compute nodes, and 3 storage nodes. So the tentative working name for this is a multiverse from nothing, but I'm open to suggestions. We've also modified the networking a bit. So, rather than having a single all-in-one bridge, we've actually got three bridges: provisioning network, a cloud network, and a management network. So the management network carries the outer band, essentially BMC traffic. The provisioning network is where we provision the cloud hosts, and the cloud network carries everything else. So that carries the APIs, storage, etc. And on top of those, we've actually got different VLANs running, but we'll get onto that later. So this machine is the seed, and let's see if I can type tonight. We can see that we've got 2 containers running. The first is called Bifrost Deploy. That's our Bifrost container. And the second is a Docker registry, which we use to host a single set of images rather than going out to Docker Hub every time. Now, I'm going to exec into the Bifrost Deploy container with a shell. Now, I know that I did state that these were application containers earlier, and I have to apologize. This one is not. So Bifrost is a set of Ansible playbooks. It doesn't really support containers right now. And Collar created a container image which would run systemd and all of these processes. It's not pretty, but it does work for the time being. So using the OpenStack CLI, we can look at the nodes that we have enrolled in Ironic. We've got our 3 compute nodes, 3 controllers, and 3 storage nodes. They're all powered on and active, so this cloud has already been provisioned. So from there, let's hop to the first controller. And we've got a few more containers on here. Let's see how many we've got. 31 containers. So every OpenStack service in this case has its own container on each of the controllers. We've also got the supporting services like MQ, Memcache, MariaDB, Keep Lively, HAProxy. Even Crony and Cron are running in containers in this case. Let's peek into one of the containers. Python directory. You see color glance API, and that contains two things. First of all, is this config.json file, which defines the command to them, and config files to copy and paste in the container. And in this case, we just got this glance API file, .conf file, and that ends up being this file, which is bind mounted into the container. So on startup, Collar will copy that file into place and give it the appropriate owner and permissions. And this is just our familiar OpenStack configuration file. Let's exec into the glance API container. We've got a dominant process, which is our init system. And that is our signal handling for us. And we've got glance API. Because we're not root, we can't change to this config files directory, but this is the source of the configuration files that are bind mounted into this container. And they actually end up, as promised, here. As we know, containers are stateless, which does present some problems when working with stateful services. So to get around that, we use Docker volumes. And these named volumes are basically this directories in there that get bind mounted into the containers. This collar logs one in particular, we useful. So we've got that linked to varlog collar. And that's quite nice because that means we can access the glance API logs from the host. Got this fluentd container, which reads in the files and processes them, parses them, and sends them off to Elasticsearch if you've got Elasticsearch enabled. Let's hop onto a compute node. It turns out this one's running containers as well. And it's quite interesting to see that we've actually got node libvirt as a container. So libvirt is running inside a container. We do need to use a few special tricks to make that work. That container runs in a privilege mode, and I think we have to use the host PID namespace to ensure that the VMs outlive the container. that this thing is actually useful. We've got a server running and a floating IP, and there it is. So that's pretty much all I have to say. I'll just finish off by saying, if you're interested, please do get involved. We've got documentation for KOB and Collar. Various different ways to try both of those tools out in the documentation and in this Universe from Nothing tool. We've got some demos on Askinwa under my username. And if in doubt, please join the OpenStack Collar RC channel and say hello. Thanks for the opportunity to talk this evening. I hope it was interesting to you all, and I'm really looking forward to seeing Belmiro's talk next.
Thanks, Mark. That was really good. I posted a question to the comments, but obviously you haven't seen it. When we do an upgrade, you mentioned about saving the state, and then you predict the upgrade state, and then you do a comparator, basically a diff between the two. Is that still the process? You just basically have to track through the diff yourself, just sort of have a look and see what the changes are and see if they make sense? Or have you got any kind of tools around checking the validity of that or anything yet? Or common errors or anything like that?
We haven't got anything like that yet. I think it would be a really nice addition to the tool to be able to, particularly as the systems get larger, to be able to collapse that data down and show you the parts that are actually different. It's on the wish list.
Yeah, yes, indeed. Yeah, I mean, I must say that was just the one bit of the process of upgrading that I thought, this could be improved a bit. It's easy to miss something that's important in a long diff, basically. So,
but it's also something that you don't really get with any of the tools. So although it is a bit clunky, it's better than nothing. Yeah,
absolutely, completely agree with that. Yeah, plenty of tools I've used where you just cross your fingers and hope.
Yeah, and we caught some things with that.
Yeah, exactly.
We got a few issues with that, didn't we? So it was pretty handy.
It was pretty handy, yeah. Yeah, I would say, other tools can claim full automation and all the rest of it, but you are pretty much crossing your fingers and hoping for the best. And that's not great if you've only got one environment. It's fine if you've got a development environment and you've got something to test on first and you can check everything out. But if you've only got the one environment to manage and you have to cross your fingers and hope it's not going to go down, that's not exactly satisfactory, is it? But,
really.
It's good to be able to see the difference before you hit the push the go button. Yeah. Anyway, thanks very much.
Yeah, really good talk. I do want one question. Early on in your talk, you mentioned Baron, which I'm not very familiar with. You mentioned that there's some features in Baron which still outperform Ironic, or there's some things you can still do with Baron, which do you know what those are, or are they very, very key or offhand?
So I think it was mostly around partitioning and setting up LVM. So a pretty powerful way of passing in an arbitrary partition format and saying, I want these disks partitioned in this way, and then put LVM onto these ones. A volume group here and volumes here. I think the reason why it didn't go further is that the integration with Nova was quite clunky.
Right.
And that's always been the sticking point. Getting something having a way to pass through this data, this information from Nova to say this is how I want my machine to end up, in a sort of a cloudy way that doesn't assume anything about the layout of the machine that you end up on, or doesn't assume too much, at least. You know, the user just wants to be able to pick a flavor and have that allocated from a pool of nodes and then provisioned in roughly this way, but not necessarily exactly.
I must say my biggest want was being able to deploy with software RAID automatically deployed on customer servers when you're doing a bare metal tenancy. It would have been nice if that was in Ironic, and I know there's been some moves towards that, but it's not. It's certainly not there yet, really, is it? And I'm not sure it ever will get there, because it mostly depends on the hardware of particular manufacturers and having a hardware driver built in for that. Whereas I'd probably go down the route of saying we'll just use the Linux kernel to create a software RAID on two disks and avoid the hardware lock-in. But what's your opinion on that?
If you pull down, I think, Train, Ironic, then it's got support for software RAID. So exactly as you say, you can, during provisioning, it will set up a software RAID on the disk. I think you have to wait till Yuzuri for that to be really usable. I think Train was more of a kind of a proof of concept phase. Might depend on exactly your scenario, but and that's been driven by CERN in the main, with a few other interested parties. We've given it a try. Doug's tried it, and I think it's been a little bit of a bumpy ride on Train, but he did get it to do what he wanted in the end, which is really good.
Okay, so it's getting there then. It's getting that feature. Yeah. Okay. Cool. Excellent. Thank you.
So what about, so there's an interesting comment in one of your slides fairly on about how OpenStack isn't cloud native. What about coming at it from the other direction? So it seems like there's been a resurgence or a sparked an interest from the cloud native community back into bare metal quite recently. So there's some interesting projects that have sprung up. So Packet, for example, have finally open sourced their bare metal provisioning system, Tinkerbell. There's projects like Metal Cubed to use Kubernetes to deploy bare metal, and that was originally based on Ironic. Have you had a chance to evaluate any of those? Do you think we'll sort of somehow converge in the middle eventually, somehow?
Yeah, it's an interesting space. There's definitely room for a Kubernetes to grow a bare metal provisioning arm, something like Metal Cube, that allows it to sort of grow and expand over a set of bare metal machines. Metal Cube looks interesting. Red Hat are pushing that pretty hard at the moment, and it's nice to see that they're using Ironic to do that, reusing an existing tool that dear to my heart. So I think that's one to watch. I think it's still focused on Kubernetes and deploying a set of infrastructure for Kubernetes rather than getting OpenStack involved anywhere. But I guess we'll see where that goes. And there has been talk of, I think Project Teapot was the name, in the OpenStack ideas repository. So Zane Bitter. We've got a detailed architecture for a cloud, picking out pieces of OpenStack, notably without Nova, but all the bits that you need to run underneath Kubernetes. So Cinder, Ironic, Keystone. Worth a read.
Cool.
Watch this space, I suppose.
Yeah. Yeah, it'd be interesting if the two communities could kind of collaborate with one another, because it seems like you see a lot of folks on the cloud native side maybe reinventing stuff or not necessarily picking up on lessons that are that had been learned and hard won on the OpenStack side. It's like, oh, that's the thing that's already been solved over here, but that's a classic open source not invented here syndrome.
It wasn't written in Go, so
yeah, it also part of it.
Yeah.
I hear Rust is the new hotness. Goes so 2019. Cool. I haven't seen any other questions come in. So we'll move ahead with the next talk then. Thanks again, Mark. That was awesome. I really enjoyed it. As you know, I'm a big fan of Collar Ansible and all the work that the Collar project does, as well as KOP itself. So yeah, it was really awesome for you to come along and give that presentation tonight. Much appreciated.
Thank you for having me.
All right, let's juggle this around a bit then. Hey, Belmiro.
Hello.
Hopefully it's not too late for yourself, and thank you again for joining us.
It's okay. Thank you for having me. So I think I can start.
Yeah, in that case, we'll hand it over to yourselves. Yeah, please, by all means, take it away.
Okay. So my name is Belmiro Moreira. I'm a cloud engineer at CERN, and I would like to talk about the 10 years of OpenStack at CERN. So a little bit of historical context here. First, virtualization and server consolidation. I think everyone started to look into this during this time. So in 2008, 2009, all the applications in data center at CERN they run it mostly on top of bare metal. This was normal at the time. People start experimenting with virtualization, but small projects. Just a reminder, AWS EC2 was released only on 2006, so we are not too late. Also, 2008, 2009, 2010 was when the LHC was turned on. So we expected a lot of requests for all kinds of users for compute resources, and we needed an efficient way, a fast way to provision those resources. So that's why we start thinking, how can we improve this model that we have? At that time, if a user needed some resources, he needed to make a formal request. It went through all the procurement purchase model, and it could take up to 1 year, actually, to the end user to get access to the resources. So, of course, this was not agile at all. We wanted to improve this, and to solve this, of course, at that time, virtualization and cloud computing sound quite attractive. Virtualization, not only for server consolidation, and of course, doing server consolidation, reducing costs, but also to have a more flexible infrastructure. So at CERN, our compute resources have two main use cases. One is the batch system that we use to process all the data from the LHC and many other experiments, and also to run services, all the applications that the lab needs daily. So it's natural that at that time, this was 2009, we came up with two different virtualization projects, basically to try different projects, different virtualization technologies. One for the batch service and the other for services. I was involved at that time with both, and I would like to describe them a little bit because this gives a little bit of context about the OpenStack at CERN. So the batch system, we look at how to virtualize the batch system, and this is a big infrastructure. This is thousands of nodes, bare metal nodes at that time. So how can we virtualize this? And the goal at that time was to have a more flexible infrastructure, easy upgrades, security updates, and so on. We looked into two different products. One, it was open source, it was OpenEvlon, and the other was commercial, the platform ISF. We are running in the batch system LSF, so it was natural to try that commercial product for us. We did pretty extensive testing of these two tools, huge scalability tests for that time. We were able to run more than 16,000 virtual machines in 500 compute nodes. This is in 2010. So huge scalability tests. All of them were running on Zen hypervisor. At that time, KVM was still under heavy development, so Zen was the choice at that time. So at the end, we continued to run these small, at the end we reduced the number of nodes, and we moved this into production with a small number of nodes, basically to evaluate. At the same time, we looked into services, how to run the service VMs for normal applications. And in this case, we look into Microsoft System Center Virtual Machine Manager. That was a tool from Microsoft to manage virtual machines like VMware style. But we built on top of it web interface. And the users were able to log in into that web interface and interact with the service, basically to create a VM, select between a Windows and a Linux image, and create that VM. And this was a very, very popular service at that time. You can see in those graphs, it's very hard to see because the numbers are very small. But in two years, we went through 340 virtual machines to more than 2,000 virtual machines, a mix of Windows and Linux virtual machines. Of course, this was a Microsoft product. The hypervisor was Microsoft Hyper-V. So this was 2009 till 2011. However, we wanted to consolidate these projects. It was clear that people really liked the self-service model. We really needed to automate all of this. But not only that, we are still managing the data center with tools that we built in-house years ago. And that was fine because when these tools were developed, there was no alternative in the market. There were no open source alternatives for monitoring, for configuration management. So we built everything ourselves. And 2011 was the time that a lot of open source projects pop up. And we decided that we needed to get involved into all these open source communities and benefit from all these open source projects. That included Puppet, Elasticsearch, Flume, and many others. With that, we call it the Agile Infrastructure Project, where the goal was basically to refactor the way we manage the data center and also introduce new tools and the cloud infrastructure. So we are lucky because during the same time frame, it was when OpenStack was released. By the way, you see that this presentation is made from different slides. Basically, I picked different slides that we have been presenting over the years, and I built this presentation. This is like a historical review. And what you see here is my first presentation of OpenStack. And I gave this presentation on January 2011. And it's quite funny now go through these early presentations. So when I did this was based on Austin, the first OpenStack release. I'd like to remind you that there were no packages to install this, needed to be through the code. And there are only two services, Nova and Swift, nothing else. And it was quite funny because to create a user, you need to use Nova Manage. Also to create a project, it was Nova Manage. Uploading an image, it was funny times. There was no a real API. You needed to use basically OK tools, and it was basically a wrapper, more or less, from EC2. It was funny times. I presented this at that time to my team at that time, and a few weeks later to all the IT departments. And it was quite clear for everyone that's looking into this project that, considering all the companies that were supporting after a few months this project and all the enthusiasm of the community, that probably this will be a very good fit for us. Again, a funny slide. So this is one screenshot of Horizon, and this was the early Horizon. Horizon was only released on 2012 on the SX release with Keystone. But this is an early screenshot of the code running before being officially released. It's quite funny that I discovered this in some slides. So we decided that to build our cloud infrastructure, we go through OpenStack. So we did initially small prototypes, but we needed to have user feedback. It was important for us to understand what our users wanted. And we have a lot of users. CERN community, at least on the site, is more than 10,000 users. So it was important for us to get feedback. So we decided to build prototypes, give them to the users, get feedback, and then destroy them and build a new release. And again, get feedback, destroy it, build a new infrastructure with a new version, and so on. And it's important to remind everyone that at that time, the release cycle was 3 months. So that's why we needed this very fast iteration. So the first prototype that we built, that we gave to the users, then we start using code names. We named it Guppy. It was based on SX because it was the first release with Keystone and Horizon. Things were getting better. It was only few nodes, but gave us a lot of experience. Then we destroyed everything. We created a new infrastructure from scratch. We call it Hamster, a bigger animal. That one was based on Folsom. We start trying with different virtualization technologies. From the previous projects, we were running Zen and also Hyper-V. But at that time, KVM was very mature, so we moved to KVM. So from early on that we start having an infrastructure supporting 2 different hypervisors. Finally, we destroy everything and we build a new infrastructure, much more nodes, a few hundred nodes at this time. Again, from scratch, we call it IBEX. And also it was based on Folsom. With this release, we try to integrate everything with all the work that other teams were doing at CERN, the configuration management that was working on Puppet. We started to build initially our Puppet manifests for OpenStack. Only later, only later the Puppet modules for OpenStack appear, and also integrated with all the new monitoring system. It was a lot of work at that time. And finally, Grizzly was released, and we are in 2013. So, and it was in July 2013 that we released what we call our production infrastructure. And we actually do this distinction because, as previously, we destroyed everything and we create a new infrastructure from scratch with no VMs, everything clean, and we gave this to the users. Now with the promise that we will not destroy their VMs anymore, and we will support this through the years now. So we are in 2013, our production infrastructure. It was based on Grizzly, and we started from the beginning with 2 data centers. So we added the data center in Geneva, and we added a new data center in Budapest, in Wigner. So from the beginning that we used both data centers for OpenStack. There was a lot of discussion at that time if we should use different regions for these different data centers. We decided to use cells instead. Why? because we wanted the infrastructure to be easy for the users, to be extremely transparent. And adding regions implies to have different endpoints, and we didn't want that. So we decided to go through cells instead. And I remind you, this was cells v1 at the time, which was a huge challenge to run. It was our first release, so we believed in AJ infrastructure. So all the control planes were replicated. Also, we made the mistake to deploy ceilometer. We thought at that time that ceilometer metrics were important for us, and we could manage ceilometer at scale. There was a lot of work integrating OpenStack with the existing systems, like the networking. So plugging OpenStack and making it play with the CERN network was a huge effort. And actually, also integrating with the accounts was another major step. Integrating with the monitoring system. And I mentioned here Glance with Ceph backend. I took these slides from a presentation that I gave in Hong Kong. But when we released on July, Glance was backed by AFS, actually, not Ceph at that time. And we started experimenting with Cinder when we had Ceph available. Because initially, with Cinder, we were using LVM. Telling the users that their volumes, that was only for test, and their volumes could disappear. As a load balancer, we still have a JProxy. Basically, very little changed in that domain. Again, this high available infrastructure, 3 masters for each cell. And at that time, we believe in big cells because we thought that if we have a big cell, it will be less work to maintain it. So we had cells with more than 1,000 nodes. And from the beginning that we thought that having availability zones was important, even if they were not really real availability zones because they were not isolated, but having the logical concept for the user for availability zone, we thought it was important, and it was there from day one. Right-time queue, again, the mistake of having high availability. At the time, we had mirror queues, rabbit clusters, at least 3 brokers per cell. It's funny now to look back into this infrastructure because during these 7 years, a lot have changed. Again, a few architecture diagrams. You have an architecture overview. So all the load balancers were in Geneva, then the top cell controllers also in Geneva. And then we have for each cell, for each data center, we have the controllers in each center and all the compute nodes. At that time, we also thought that having Glance in each data center was a good idea. Glance with cache, we thought that would be a better alternative, accelerate the data transfer, the image transfer. Turns out that we removed that fast. In the other slides, you see all the components that we deployed at that time in a logical order. It's funny now looking back that we deployed StackTack also. That was a tool developed by Rackspace to get metrics, and at that time it was quite useful. Some graphs showing the infrastructure at that time. So in the number of VMs graph that you have, you see the prototypes. You see that we had a lot of VMs running, around 2,000 VMs. Then we destroyed everything. We deployed the new infrastructure. So in that case, we named it IBEX. The number we gave it to the users. The number of instances starts to grow up again because they are testing. Then we destroyed everything. And the last part is when we went into production. And since then, we never destroyed the instances anymore. Also, you see the number of users that tested the infrastructure. We had around 100 users testing the initial prototypes, and then the number started to increase when we moved into production. So looking back again to 2013, we have the numbers of nodes that we had at that time. And looking back now, at that time, these looked huge. In Geneva, we had more than 300 nodes, and in Wigner, almost 300 nodes. In a total of VMs of 2,000 VMs after a few months of being in production. And believe it or not, at that time, these were big numbers for us. This is the number of VMs, the cumulative number of VMs that were created in our cloud till 2017. You see that we reached 1 million VM in February 2015. And the other plot shows the number of VMs actually that are running the infrastructure. Currently, we have around 38,000 VMs. So we are in production since Grizzly. Since then, we have been upgrading every 6 months, and we are introducing new features, new projects into the infrastructure. So in Grizzly, we started with Nova, Glance, Horizon, Keystone, and also Salamter. And since then, we are adding more and more projects. You can see that we introduced Cinder, actually in Icehouse, almost 1 year after we moved into production. Then we start experimenting with ETH and Raleigh. In Liberty, it was quite important because it was the first time that we start experimenting with Magnum and Neutron. And they were released into production in our infrastructure in Mitaka. It was also in Mitaka that we made the decision to remove Salamter from the infrastructure. And since then, if we go through to Rocky, you can see that there are some projects that we start testing and then they were removed. For example, Trove and Morano, they were evaluated, but they never had a big community traction. So we decided that it was not worth to deploy them. And currently, we are looking to Watcher. Again, a very little community behind, and Shilling for functions as a service. Let's see. I didn't add the other releases because since then we are quite stable. By the way, we are not in Rocky. We are running actually a startup upgrading to Zuri. So I'd like now go through some highlights that we had through all these 7 years. I'll start with Nova cells. So cells allow Nova to scale to thousands of compute nodes. It's like you are sharding your infrastructure. You can have a failure domain, but not all the infrastructure is affected. If you have a problem in the control plane, probably only a few nodes in that cell will be affected. So we really like it from the beginning, this architecture that was developed by Rackspace, and we deploy it. In Cells v1, there were very few deployments using cells. So it was a very small community, but thankfully the community saw the value of having this sharding to scale and develop from scratch Cells v2. So over the years, we moved from these initial 2 cells to more than 70 cells today. And in 2018, we upgraded from Cells v1 to Cells v2. And that was a huge upgrade, moving all the infrastructure from one architecture to a completely different architecture. Salamter. So from the beginning that we deployed Salamter, we had a lot of open Salamter to collect all the metrics that we required. However, managing Salamter was extremely complicated. You can see that Salamter architecture, that was our architecture that we were running. And you can see all the pieces, all the databases required that we are running to collect metrics. And the biggest problem was at the end, after collecting a huge amount of data, it was extremely difficult, basically, to collect the usable things from the API. It was almost impossible because all the amount of data. that we were collecting. So 3 years after running Ceilometer, we decided to remove it, and to replace it, we developed a sensor for our monitoring system that talks with libvirt in each compute node and collects the metrics that are of interest to us. A small piece that we kept from Ceilometer was the notification agent, because there was no better way basically to collect all the notifications from the different services. On storage, so we are running basically from the beginning Cinder with LVM, but that was not reliable at all. So we only say that Cinder went into production when we had Ceph as a backend, and that was in 2014. From the beginning that we had several volume types available, and later we introduced other storage options like OpenStack Manila in 2017, when CephFS was finally available for production. And more recently, we introduced S3 also on top of Ceph. In terms of containers, so we did a huge investment in container orchestration. Our users wanted to have an easy way to deploy Docker Swarm, Kubernetes, Mesos. So Magnum was really important for us. At the beginning, we were able to deploy all these kinds of clusters. However, over time, now we have more than 500 clusters deployed into production, and most of them are Kubernetes. So Docker Swarm and Mesos almost disappear as our use case. But it's a very, very popular service, growing every day at CERN. In terms of networking, of course, we started in 2013. So at the time, only Nova Network was available. So all our architecture, the integration with the CERN network, everything was done in Nova Network. So then we had Quantum, that changed to Neutron. And the way it works is completely different from Nova Network. So we needed to make a huge effort, again, to integrate Neutron with the CERN network. But then we have this critical component of this network that was working fine. And we also had a new project that we needed to migrate, because from early on, Nova started to announce that they will deprecate Nova Network. So we introduced Neutron slowly in our infrastructure. When it was deployed, we start to deploy only the batch compute nodes into Neutron, basically to gain experience, and because it's not such a critical workload like services. And we got more experience, and since from some time that all the new hardware that we add into the cloud infrastructure runs on top of Neutron. However, we still keep a lot of hypervisors in Nova Network, and actually is the ones that have the critical workloads, the user applications, and for the CERN services. So we are still fighting now that Nova Network was deprecated already a few releases ago. How can we migrate from Nova Network to Neutron? We have a procedure, we try it, but it's really scary doing this. So we are still sticking with Nova Network for now. We have the plan to migrate. So let's see. The problem is that Nova Network is not supported anymore. So every release, every time that we upgrade, we have a lot of patches that we need to integrate into our release to continue to support Nova Network. Bare metal. So we come from 2009, 2010, when we wanted to move away from bare metal. And we wanted to have everything into VMs. Turns out that there are a lot of use cases that require bare metal, and runs much better on bare metal than in virtual machines. So provisioning bare metal in a consistent way using an API was quite attractive to us. And with the OpenStack Ironic, we started looking deeply into this project, and we deployed it in 2018. And we decided that all the hardware that we have in data center should be enrolled using Ironic. Even the hypervisors in the cloud infrastructure should be enrolled using Ironic. So now all the compute nodes that arrive in the data center, first they are enrolled in Ironic that runs in the clouds, and then the hypervisor, it's Ironic nodes that will get VMs, user VMs. So we are in the process to enroll the old hardware. Currently, we have more than 5,000 compute nodes enrolling in Ironic, and we are looking to the end of this year, beginning of next year, to finish enrolling all the hardware that we have in the data center into Ironic. And the big advantage with this is basically the APIs, be able to control everything using an API. In terms of operations, we start playing early on with Rundeck. Rundeck allows you, having a web interface, to execute jobs, basically simple scripts. And that is quite important for operations, for maintenance reasons. We have a series of Rundeck jobs that are used by the repair team and many other teams, that when they need to, for example, intervene in a node, they run the Rundeck job that basically will remove the node from the scheduler. It could migrate to the VMs, and then the repair team could actually intervene in the nodes. And basically then, when they are finished, they can add the node again into the infrastructure running another Rundeck job. And they don't need to know anything about OpenStack. This is completely automated for them. So later, we also introduced Mistral. And Mistral, because it's completely integrated with OpenStack, it's very powerful to run workflows. We use it for the project creation and code updates in our infrastructure. Operation fun. So over the years, we had many fires in infrastructure. But the one that I want to recall was the meltdown Spectre L1TF in 2018. This affected everyone. And when you have a large infrastructure, it's very hard to manage all of this. And you basically cannot intervene without affecting your users. So in our case, we needed to patch and reboot all the hypervisors that were running service VMs. This was around 20,000 virtual machines, affected around 1,400 compute nodes. And as you can imagine, this takes a lot of time, and it's a nightmare then when you need to reboot nodes and nodes don't come up. It was a lot of work. Thankfully, for all those operations, we divided the infrastructure in availability zones. So the way we communicate with users was telling them that in this date, we're going to reboot all the availability zone A. So if you have critical applications, please move them or replicate them in a different availability zone. And actually, that worked very well. Some other experiences during the last 7 years. Several upgrades during this journey. The release cycle is every 6 months, so as you can imagine, a lot of upgrade experience. Not only OpenStack, but also we went through OS distributions upgrade. So we needed to upgrade from Scientific Linux 6 to CERN CentOS 7. And this is always disruptive upgrades. And now we are facing a new big upgrade that is to move to CentOS 8. We are still thinking how we're going to do it. The control plane is easy. What is very hard, it's always the compute nodes that are running the instances. So as I said initially, we supported two different virtualization technologies, KVM and Hyper-V. At that time, the thinking was that we should run all the Windows VMs on Hyper-V, mainly to give confidence to the people that had the Windows VMs to run in a virtualized infrastructure, and also for support reasons from Microsoft, because they will only support your VM if it was running on Hyper-V. But times changed. So initially, all the VMs that were in CVI, that initial virtualization project that I mentioned, were migrated into OpenStack. It was easy migration because they were running on Hyper-V. So basically, this was copy the images and then instantiate again that image. And finally, years later, we convert again those virtual machines. We took a snapshot, converted the image, and created the image to run on KVM. Security updates, I already mentioned that required the reboot of the entire cloud. Also, something that we started working on very early was in automating all the operations like project creation, quotas, and so on. So regions. If you remember, I start telling you that we decided to not go through different regions, even if we had at the beginning 2 different data centers. However, our thinking changed, not really because we really needed a region logically, but because we were adding more and more nodes into Neutron. So at the beginning, we started with only one region because it was easy for the users, and cells give us all the functionality to scale the infrastructure. However, when we moved to Neutron, we realized that it's more simple to manage 2 small clouds than 1 large cloud. So Neutron, it's really one piece, one project that you cannot share shards. It's not like Nova that you can have different cells and shard that to scale. Neutron is only one project, and if that project fails, all your infrastructure is affected. And we had some outages because of that. So we decided that we have these 2 different use cases, one that is batch and the other that is services. So probably it is a good idea to split the infrastructure in 2 regions. And this will allow us to actually continue to scale, because then Neutron will manage a smaller infrastructure. So we did that. So we moved from 1 region to 2 regions, and we split our production infrastructure live into 2 different regions. That was a huge challenge to do that. For the users, was basically transparent. We created a region with the service VMs, so those users didn't notice anything. Their VMs continued always to run. And the other region was all the batch system. They also didn't notice anything in the VMs. They just had now a different endpoint to connect. Later on, last year, actually, we don't have anymore the contract with the Vigna data center. So we transfer a lot of hardware from Budapest again to CERN. And we created a different region with that hardware. So currently we have 3 regions, 2 for batch nodes and 1 for services. When you have a lot of resources, it's very hard that all your resources are being completely used. So we start looking into how can we have preemptible instances. The way that we operate is using quotas. So a public cloud basically is based on pricing. So if you have a credit card, they will always give you capacity. However, in a private cloud, our users don't pay, so we need to implement a quota system, meaning that if a user is not using their quota, means that our resources are not being used. So this idea of having preemptible instances is basically to allow the projects that exhausted their quota to continue to run instances, but knowing that these preemptible instances can be killed at any time if the users that have the right to have quota instantiate their instances. So there is nothing in OpenStack with this. So this is the spot instance concept in AWS. In OpenStack, we didn't have anything like this. So we developed this with the community. And quite recently, a few weeks ago, we deployed this in our cloud in production. And we are preparing a blog post about it. So after these 7 years, we are in 2020. So what's next? The big challenges, we want to have an even more flexible infrastructure. And we believe that if we have our control plane in containers, will give us much more flexibility in terms of upgrades and to manage the service and to add capacity in the control plane. So we are investing a lot of work on that. The other thing that we are looking at is, as I said, to enroll all the resources that we already have in data center that they are running workloads, to enroll them into Ironic without disrupting the workloads that they are running. We are looking also into GPU resources. Over the last years, GPUs are becoming quite important for many workloads. We still have resources in Nova Network, so moving them to Neutron is a priority. We have a plan. We are just scared to do it. And maybe introduce a SDN in our infrastructure. It's very hard. All of this, we have a flat network infrastructure. Introducing SDN involves many other teams. We are investigating how can we get there. Before I finish, I took this screenshot yesterday. This gives you an idea about our infrastructure. So currently we have more than 300,000 cores available or in infrastructure. A lot of users, not that many as that this graph shows, definitely a bug there. But you can see the number of projects, the number of VMs, the Magnum clusters, and so on. So as a summary, during the last 10 years, the resource management and deployment model changed completely. We went from virtualization to server consolidation to a cloud infrastructure. Also from bare metals to virtual machines to now managed bare metal to containers. And of course, we continue to adapt infrastructure to the new technologies and the requirements. And we continue to have this iterative approach to introduce new services and new functionality. And we are exploring new approaches to deploy and manage this large infrastructure, using Kubernetes for the control plane, introducing new regions, and also looking into other models like functions as a service. So as you saw, this was a mix of different slides from different presentations. I would like to credit the authors of all those presentations that I took the slides. And thank you. Let me know if you have any question.
Awesome stuff. Thanks, Belmiro. That was fascinating. I've got a quick question. How big is the team at CERN that runs this infrastructure?
So I always need to think about it. It's not only a team. It's several teams. So for example, network. The network of the data center is not the OpenStack team. We have a network team that leads with the routers and switches, the normal plugging of machines. The OpenStack team only cares about Neutron, for example, the Neutron deployment and the network. The same for the hardware deployment. Is not the OpenStack team that goes there to the racks and puts the servers there. So we have a team that only does that. The same for repairs. So the OpenStack team, we have a core team of less than 10 members. I think 7. I need to count them. And then we have a lot of other members that are fellows and technical students that come to the team to learn about the OpenStack, about the infrastructure, and also with a very defined project for them to execute. So normally the team with all the students, fellows, is around 15 people.
Yeah, still a lot of infrastructure for a very small number of people.
Yeah, so that kind of scale is really scary. I'm just wondering some of the biggest crisis situations you might have had over the last 7 years. What were some of the biggest whoops-a-daisies kind of situations?
Well, I remember one time that we had a power cut. It's always scary, power cuts. Other time that an OpenStack component was upgraded without us wanting, for example. That was quite scary. We are testing, for example, it, and we connected it with the production database, the test instance, and we just run the normal sync, database sync, thinking that we are playing with a dummy database. It was production, and we then upgrade the service. Of course, we cannot go back. So little things like this, of course, happened during these 7 years. We had an issue at the beginning that we are automating things with a script, and there was a bug in the script that started to delete glance images, for example. This was a long time ago. It was quite funny to recover then.
Cool. Nothing out of this world in terms of cloud bursting, cloud crashing kind of situation though. Sounds like you had a few close calls, but nothing disastrous.
So of course, infrastructure like this, every day there is something new, something that we discover. Sometimes we have small API outages that we need to investigate. What happened? But those are normal things. I don't see a major issue that we had in the past. Also, the architecture that we did from the beginning is quite resilient. As I mentioned initially, then I didn't explore that, but initially we had high availability for everything. We removed that over time because it's much in the kind of use case that we have. If the APIs fail for a few moments, is not critical because VMs will continue to run, all the services will continue to run. So having high availability is quite expensive, and the probability that that thing goes wrong, the cluster rabbit, imagine that we have 70 cells. If we need to have a cluster rabbit for each cell, the probability of that thing to fail is so high that it's better to not have high availability at all and have only one rabbit for each cell. So we simplify our deployment in every aspect to avoid issues.
So does that mean that you have single rabbit cluster nodes? Do you have any underlying sort of RAID on the servers and any redundancy at all, or is it just a case of rebuild from scratch if it goes wrong?
So for the compute nodes, we have RAID 1. So that gives some security for the VMs that are running there. For the control plane, actually our control plane runs in virtual machines deployed by OpenStack. So we have this inception. And if the control, and we have a lot of VMs, we have high availability, for example, for the APIs because it's a stateless service. So we can have a lot of virtual machines for the OpenStack APIs. We have a lot of virtual machines for clients, for example, same for Keystone. If a compute node goes down where these VMs are hosted, many others will be up, so the service will not be affected at all.
But what about RabbitMQ specifically?
So for Rabbit, we have one big Rabbit cluster that is, of course, for Neutron. Actually, we have two now because we do this per region. That one, of course, is we have a cluster, Mirror queues, because it's only one component. But for Nova, for each cell, we only have one RabbitMQ for each cell. To be more precise, we only have one VM acting as control plane for each cell. And that VM contains the Nova conductor, RabbitMQ, and the Nova API service for that particular cell.
Okay, yeah.
If that controller goes down, means that users will not be able to interact with that cell. However, the VMs will be running. Their applications are not affected. And we have a lot of hot standby VMs ready that if something happens, we just configure that VM that is already running to be a new controller.
Yeah, okay, that makes sense. Cool. Thanks.
Cool.
Well, thank you very much, Gulmira, for that talk. It was really...
Thank you. Thank
really
you for having me.
Thank you.
Cool. I think that's it then. Should we wrap it up?
I think so.
A huge thank you to all of our speakers tonight for donating their free time to impart some awesome knowledge upon our community. It's obviously, you know, one of the upsides of virtual meetups is at least that we can have some speakers from international locations that might not otherwise be able to attend. So it's a shame we can't all be together to head off to the pub now for a couple of drinks, but at the same time, it's fantastic to be able to embrace this medium in this format and take advantage of it with some talks like the ones we've had tonight. So yeah, thank you again to our speakers, and obviously thank you to everyone that's attended. And I guess we'll leave it there. We'll probably try and line up maybe another virtual meetup at some point soonish. Yeah, we should probably do that. Get our heads together and organise something, and stop being lazy. Hey, Daryl, now you're between employments. You've got all this free time on your hands.
Yeah, remember, primary school teacher. That's,
yeah.
Except the school holidays now. So.
Teach your kids how to organise meetups. That's what you should do, and then they can run all this for us.
Well, maybe we need a new application instead of a virtual meetup, a virtual pub, so that we can have that afterwards.
That's a good idea. That's a good idea.
All right. Well, thank you.
All right, then. Thanks, folks. Have a good one.